in General Physics 1. So our game is called Bring It On. It's actually a physics sandbox that is available in iOS devices.
I'm sorry. Can you go online and then share the slide? Connect the Google Meet and then share it so that online people can see it. I'll send it to you. Right? So there are two more chairs here. You can sit down and then two more there. I mean, you guys don't need seat, right?
No, you can take this one.
Yeah. Just
And there's another two
just
here.
come here. Here.
Yeah. VIP road. There.
Yeah, just come in.
No requesting.
This is automatic, no? Yes. Are you in? Okay. Microphone, can you use this one?
Yeah.
Here's the microphone.
So shall we continue?
Yes, please.
So as I was saying, Bring It On is a physics sandbox game. It's available on your iOS and Android devices. So this is the content of our presentation. First, I'm going to introduce our team, then the introduction of the game levels. So there are like multiple levels in the game, but we're going to introduce like some that are really interesting. Then you guys can try out the game, and we're going to explain the physics behind the game and the conclusion. So the team itself is just three of us. This is Olivia, Rogelio, and I'm Jason.
You're Jason. Okay.
Yeah. So for the game introduction, I split it into 6 parts. First, the overview, and then the objective, the mechanics, solutions, difficulty, and rewards. So in a nutshell, the game looks like this. You can draw objects, and it's a sandbox, basically. So the objective of the game is players must complete specific objectives in each level. So in each level, there's like a drawing or a text in each level. So the game tells you guys what to do. So it involves physics-based challenges and creative problem solving. And then the game core mechanics allows you guys to like draw shapes on the screen and then interact with the objects and find solutions to the puzzles that is given. Next is the solutions. So the game encourages creativity by offering multi-ways to solve puzzles, allowing players to experiment and find their own unique solutions. So in each level, there are like many ways to solve the puzzle itself. And then the difficulty. The game's difficulty escalates as the player progresses through each level, introducing new challenges and elements to keep the gameplay more engaging. And then rewards. If you guys are like very competitive, so the players that play the game can earn stars for efficient solutions and compete on leaderboards to challenge friends and other players.
Okay, now I will talk a little bit about like the physics that we can find in the game. So the game try to simulate the laws of physics as accurate as possible. And one of the main concepts that you can use to actually solve the puzzles are, for example, gravity. If you, for example, make a drawing or a shape from in a high place, this one is going to experience free fall, friction, and inertia. So you can see the little ramp over there. The same happens in the game. If you draw a ramp and then put a little object, it's going to experience circular motion or dependent what kind of shape you draw. There's going to also be friction. So for example, if the surface is not so like if there is some rock kind of shape on it, it's going to experience some friction. Collision, many times you're going to use this concept to actually move other objects using the energy of the original one. The mass and the weight, you can draw shapes in many different, you can make drawings or objects in many different shapes, and you can add weight to it by making them either bigger or smaller, and rigidity. This one means that all the objects that you make are going to be rigid. That means that, for example, you cannot use springs or any other elastic kind of materials. So here, I mentioned earlier, gravity simulates gravity, friction, and inertia. How object interact with the surface. Next one. The collisions, we're going to explain a little bit more about this concept later. The mass and weight. Of course, heavier objects require more force to move. Lighter objects require less force. And the mass is determined, as I said, by how large or dense the object, how dense you draw the object. And rigidity, same as I said before.
Okay, so now we're going to let you guys try out. The first one is level 7. So what do you guys, you guys want to try out?
Please raise your hand if you want to try out level 7. Anyone?
Wait. There's no one else?
The guy in the back wants to try.
Oh, okay. Let's go to the student.
But I don't think he can do it.
It's great. And the next one, we also can let you guys try out level 20. Can anyone raise your hand if you want to try out?
Don't be shy, guys. Okay, professor here.
Or how about Professor Hashimoto?
Yeah, of course.
So can he try on the screen so that or we cannot? Can you join on the Google Meet and then share the screen? So or can we try with this laptop so that people can see how he fails?
Jason, come here.
Can we try on the laptop?
Yeah, sure.
Then we can see, what's going on.
Actually, I forgot to bring my external hard drive where the game consists in the emulator. So.
Oh, okay. So you have to be app. Why don't you join a Google Meet and then share the pad screen? Then. So level 7 is cleared or?
Yeah, we.
No. The guy in the back failed to do it.
Oh, so do I have to come in?
No. We will provide the solution to them. But you want to
Okay. No, it's okay. Go ahead. 重いですよ。10分ぐらいは最低でもスイッチしたい感じ。
あ、わかりました、わかりました。まあ、時間調整してみます。そう、意味が。
So what's the name of the game?
It's Bring It On.
Bring it on.
Yeah.
Like it's like a word game. Bring it on.
Okay. So what should I do? Objects in a small box.
Yeah, you draw objects here in this part.
Okay,
And
like
then
that.
You need to move the object into the right part.
You need to put something in the red part.
That's impossible. That's impossible because there's only gravity, no?
Oh, you can.
There's many other concepts, maybe like simple play.
I mean, there's no way, no? Oh, I see. I can do. Oh, I can do. I can do a lot of them, and then some.
Yeah, you can get very creative with it.
This works, right? Okay, almost. So I need something here.
Oh,
Yeah!
yeah.
Succeeded!
Yeah.
Yeah.
This is why I'm not. Okay.
So that's level 7, and there are like other levels.
And the last level we want you guys to try out is level 30. Anyone want to try this level?
You sent me the Google.
Maybe we can for the solutions.
So the solution for level 7 is quite simple. So we use, what is it like? So we use a concept that is called a seesaw, if you guys have heard of it. It's a first class lever. And in this solution, I modified it to make it as a catapult. Sorry about that. So well, we use a seesaw for the object over here and put a heavy force. So
Oh, that's beautiful.
yeah, thanks. So there are many types of lever, but on this solution, we're using a first class lever, which is the seesaw. So the wooden board, this is like a diagram of the seesaw. The wooden board here is the lever arm, and the blue thing on the bottom is the pivot point. So on the catapult seesaw, there's we can divide the arm by two sections, which is the effort arm and the load arm. So on the object force, on the effort arm, we push an object force. So the projectile on the load will provide a motion.
Sorry, can you mute the microphone of your? There's a little bit echo.
So here's the explanation of the simple machine. So it's a lever. Seesaw is a simple machine that allows the rotation of an object around a fixed point. And this fixed point is called the fulcrum, which is the pivot point that an arm is mounted on the fulcrum. So it allows the arm to move freely. And when there's a lever, there's always a mechanical advantage. This is the measure of how much a lever amplifies the force. You can get this by dividing effort arm length to the load arm length. And then there's a force transfer. So when a effort arm is affected, the load arm will also be affected. So the force affected on the effort arm will be transferred to the load arm, where the formula will be the force of load arm equals to the mechanical advantage times force of effort arm. And then when the effort arm is like pushed down, so there will be an excessive of force transfer, which causes the projectile to launch. And this launch projectile follows a parabolic motion. You can get the formula of the horizontal motion, which is like the max distance is the initial velocity square times sine 2 theta. The theta here is the launch angle divided by gravity. And then you can get the h max, which is the maximum height the projectile can achieve by using initial velocity square times sine square theta divided by 2 times gravity. And you can calculate the time for the projectile to reach the h max by using initial velocity times sine theta gravity.
So next one is level 10. One of the solution is by using mass, and then I drop it to the lever, and then the lever make a motion, which then make the jar move, and then the ball gets out. So for the scientific explanation, the first one, I'm going to start with gravity. So gravity is a force that pulls all objects with mass towards one another. So here's the formula for the gravity. So gravity here is responsible for the free fall of the objects near the Earth's surface. And in this case, to generate the force, I use the gravity by dropping some mass to the lever. And now let's consider the kinetic and potential energy. As an object is released from a certain height and allowed to fall freely under the influence of gravity, it undergoes a certain transformation of energy. At the start, the object possesses a potential energy, and then when we drop the object, it transforming become a kinetic energy. Now let's move to the torque. So torque is a force that causes an object to rotate around an axis, and in this context, we focus on the levers and their connection to the torque. By applying force to the torque and by applying force to the lever, we set them into a motion. And the last part is rotational motion. Rotational motion involves objects spinning or revolving around an axis. And our focus in this level is specific to this scenario when extracting a ball from the jar, the circle jar. And to release the ball, we apply rotational motion to the jar itself, and it generates an essential centrifugal force, and the centrifugal force pushes the ball outward from the jar.
So Olivia, can you show it again, level 20, and then where is your torque and gravity, and then
So the torque is when I push the lever, and then the rotational motion is when the jar moves, and then the gravity is when I drop the mass.
Okay. So the purpose here is to get that yellow thing out of the
yellow
jar.
thing, yeah.
Okay. Okay. Thank you. Thank you.
Okay, so this is level 30. The purpose of this level is to place this blue ball here into the orange basket.
Okay.
So one interesting thing here is that these two are together. And the reason why they are together is because those are two charges that have opposite magnitude. One is positive, the other one is negative. And the interaction there, or the force that is generated, is called electrostatic force. And according to Coulomb's law, if the charges are the same, objects are going to repel. And if they're the same, they're going to attract to each other. In this case, that's what's happening there. So for this level, first I will show you the solution, and then I will explain the concepts that I found there.
Good.
Okay, so this is what I was mentioning before. I found this formula quite beautiful because it actually reminds me of the gravitational force. With the difference that in this case, the objects can repel each other or can attract each other. Gravitational force is always a bigger object basically attracting the other. Here you see same force repel each other, different attracts. Now, the formula, I will break it down. This is called the Coulomb's constant. This one is the magnitude for one of the charges, the second charge. And this one over here is the distance squared. That means that the force is proportional to the charge, and it's inverse. It's This means that the farther the objects are, the less the force, and the closer they are, the bigger the force. Now, this one, it was already explained before. Just one little thing that I want you guys to notice is this here. This M1, because we live on planet Earth, this is always going to be the mass of the Earth. This is going to be the mass of the object being attracted. This one is called the gravitational constant. So this term over here, gm1 over d squared, which is the distance, that's what we basically call as gravity. So if you notice here, this is just the same formula for like free fall, where this is g, or the acceleration, and this is just the mass of the object being accelerated. And the last part I will explain is regarding to collisions. There are three types. The first one is called perfectly inelastic collision. As you can see here, before the collision, there is two objects. After the collisions, this is during the collision. You see this part over here when they impact to each other. And after the collision, interesting thing is that what it used to be two objects kind of become one. And when this happens is when the momentum is conserved. However, there is a great loss of kinetic energy, and this is when the biggest loss happens. Elastic this is actually an ideal type of collisions because in real world there is always going to be some loss of kinetic energy, either in the way of sound, heat, etc. So what happens here is that the ideal case, there are two objects. After the collision, there are still two objects, and in this scenario, there is no loss of momentum. This one is conserved, and there is no loss of kinetic energy. And in elastic collision, which is the one that we see more often in real world, is when originally we have two objects. After the collision, we still have two objects. Momentum is conserved, but there is a little loss of kinetic energy. So can you go back to my level? Okay, so here for my solution, the goal is here there is some force generated. So I need to generate a bigger force to separate the objects. Now to redirect the trajectory of the ball, I draw a little ramp. And I made use of the concept that we explained before, the rotational movement. And in this case, to make it to the ball go inside, that's why I draw the little ramp there.
So which one of the collisions are assumed here?
In this case, you see that I draw an object and the objects do not merge with each other after the collision. So this is going to be a type of inelastic collision. It's not perfectly inelastic because the objects remain separate after they hit each other. And it cannot be completely elastic because we are assuming that some energy is going to be lost in the process.
Okay.
Okay, so for our conclusion of the presentation, one of the things that we notice in the game is that physics is pretty much everywhere, and we can learn learn about it through games. In combination with the traditional teaching style, can be an amazing way to keep us motivated and engaged.
Who came up with this plan? Which teacher came up with this plan?
Thank you.
No, I like this slide.
Um, Problem solving is a great deal of physics, and physics is not just one thing. It's actually related to many disciplines and require the integration of multiple concepts. So that one is something you can see in the game puzzles. We need to combine several physics principles to devise effective solutions and kind of mirror some real life situations that we encounter. And some final words. Again, thank you to Professor Tomo, because we learned that interactive learning, problem-solving skill, transdisciplinary connections, and the practical applications of physics are many of the areas in which we can broaden our understanding through games, in this case through Brain It On, and leave the question open of how much of this kind of approach should be implemented in future learning.
Very nice, very nice.
So it's time for our Kahoot.
Good.
So everybody go to kahoot.it, please, and we'll give you the code.
You go to Kahoot and then
So this is the page you need to access.
what's the pin?
And the pin. And 144 it's there.
Okay.
Anyone is still trying to join? Please raise your hand.
Hopefully, I think it says that the limit reached, so
Limit reach.
I don't know.
Maybe you can start now because we're not.
Oh,
Yeah, it's,
we need to pay to.
yeah, you need to pay. Yeah.
Oh,
All right, bring it on.
so what was the question?
If the momentum,
Can you include it?
if there is, okay, good. Momentum is conserved after a collision, but there is a slight loss of kinetic energy. So what kind of collision is it? 11 people were paying attention. Great. Okay, great. First place. Congratulations. Okay.
Oh.
Technical difficulties in this side. Internet outage.
Ah, I was cut off too.
Okay, we gave you extra seconds to think about it. Ah. Hey. Good job.
Internet problem. Who is hey? You?
It's over there.
Oh, good. Good job.
Hey, Jason. Very close to each other. Wow. Shan. Shan. Very close, Shan.
You have 7 more, Chris. So we need to switch to the lecture.
Oh, okay.
So maybe we can stop it here.
Yes. Maybe that's the question.
The last question.
Okay. So who is number one now? So hey is number one.
Hey, yeah.
What Sam was doing good too. You guys are good. Okay. Well, thank you very much, Group 6. I think that was a very good presentation, combining, game and physics. It was very nice, very nice. Any quick question? Was everything okay? Okay, go ahead.
What's your max level on the game?
Our
Max level you reached on the game?
let me check. I think our max level is like around
Maybe
Mine,
you can
mine 30.
40? Wow. How about you? What is your max level?
0.
Okay, thank you very much, Group 6 again. then today, we have a special speaker, Professor Hashimoto from Johnson University. He is one of the leaders on in so-called fast radio burst. It's a mysterious burst. I think you're going to talk about it.
Yes.
Okay, so he's going to explain about it, and then he's leading also building a new telescope in Taiwan. It's a very exciting project. Once it's built in Taiwan, it's going to be top research area for this fast radio burst. So he's carrying out a very interesting science. And then today, I think he will tell us about this mysterious object. Okay, let's welcome Professor Hashimoto.
Back to the next. Down.
After you finish this, you can ask whatever questions you want to ask. Like, I don't know, how many girlfriends he has.
I'm sorry, wait a little bit. So I'm checking this. Okay, this works. Okay, it's working. Okay, so thank you very much for this opportunity. So I'm Tetsuya Hashimoto from National Johnson University in Taiwan City. So today I'm going to talk about this mysterious fast radio burst. This is a topic in astronomy, so let me try to advertise my research topic. And I heard that this class is about general physics, including say, general relativity, electromagnetism, and also quantum mechanics, something like that. I try to connect some topics to these things. So then also some people may not have physics background, so therefore I try to make it easy as possible. So let me go ahead. This is my personal self-introduction. So I am in National Johnson University, which is in Taiwan City here. So actually, I was here before, 3 years ago, as a postdoc, working with Professor Tomo. So therefore, actually, we are still working together. So therefore, I got this opportunity today. So thank you very much. And then, so this is an outline of my talk today. So I hope I have time, but if I don't have time, actually, I'm okay with maybe stopping in the middle, but that's totally okay. Please stop me when time reaches. Then I'm going to introduce about this mysterious fast radio burst. And also, I briefly talk about what is the origin. And also, I want to talk about how useful it is when we try to understand the universe. Actually, this fast radio burst is very useful to understand the universe. So let me introduce these things. Then I always start with this one. So this is a typical optical image on the sky. You can see the sky with our eyes. That is optical. You can see it's optical. But you can also observe the universe using radio telescopes. Then when you switch to radio, you see the very difference, right? There's a significant difference between optical universe, radio universe. So it looks like a very different structure appears in radio. But I would say most different part is this flashing object. You can see many flashing, these fireworks. So this fireworks, recently people found this fireworks in radio. But these fireworks disappear only in 1 millisecond, 1/1000 seconds. So it's appear and disappear immediately. So therefore, it was very difficult to detect this radio fireworks before. So this is really new in astronomy now. So I am working on this radio fireworks in the universe. So this is so-called fast radio burst today. So let me keep going. This is a schematic diagram, how we detect this radio signal from the universe. Actually, we know that this radio signal is coming from extra galaxies outside Milky Way. So there is a source which is emitting this mysterious radio signal in the galaxy outside Milky Way. And then it comes to our Earth. Then this Earth is coming to us. And then this radio telescopes, something like this. These telescopes can detect this radio signal. So this is so-called first radio burst. So what's this? So okay, let me try to explain this name. Why people call first radio burst? So actually there's a meaning here. Why first? Because it disappears in almost instance. So these radio fires happen within 0.001 seconds. This is 1 millisecond. It appears and it immediately disappears. It's really flash. So this is fast, very fast. For example, how fast it is? So human's reaction speed is, for example, 0.2 seconds. Reaction. Reaction. So 0.2 seconds. Blink. So your eyes blink. I heard that it is about 0.1 seconds. So this is much faster than this. So this is much faster than this. And 100-meter running. So usually when people take a record, that minimum unit is usually 0.01 seconds. This is even longer than this flash, data flash. And I heard that this is standard. Some of standards actually the time scale is 0.001 second. So therefore, this flashing object in radio, the time scale is almost instant, which is comparable to the standard. But standard is bright in optical, but this is the radio version. It's very bright. And then radio burst. So what does it mean? The burst means kind of explosion in radio. So in astronomy, when we find something extremely high energetic explosion or high energy phenomena, so we use this burst. This kind of explosion. It's very bright. So how bright it is? And we can calculate typical total energy of this radio fireworks, individual fireworks. So we can calculate total energy. So that total energy is about 10 to the 13 times higher energy than that human uses in a year. So that's a lot of energy is released from individual this flash. That's amazing. Also, at least 1,000 LBs are happening every day over the sky. So this explosion happening in the universe. So recently, people really noticed this. Then you may wonder if this is so high energy happens, then it may be dangerous to the people in Earth. But actually, it's okay because this fast radio bursts, they are happening in distant universe. So therefore, actually, intrinsic energy very high, but it is okay because Earth is too far. So therefore, that's safe. And then I have a quick question here. I don't have time to finish everything today. So there's a quiz. Actually, I show, and there are two examples here. And then one is the true signal from the space, this FRB, fast radio burst. Another is signal from microwave. So actually, there's a famous story in this science field. Actually, astronomers really get confused between this true astrophysical source and microwave. So which do you think? Maybe you can raise a hand. Who thinks this is the true fast radio burst? Who thinks this is fast radio burst? Please raise your hand. One of them is fast radio burst. Another is microwave. Please raise your hand. Oh. I see. Oh. People who select this one, you guys have a sense of astronomy, I think. Sense of astronomy. I will explain this. Who thinks this one is FRB, true signal? Oh, it's almost half. Okay, good. The answer is, do I have an answer? Sorry, I don't have an answer. Answer is, this is actually, so this is the true signal of fast radio burst. And then usually, this is a little special. So usually in astronomy, when we detect something from nature, so usually we do see something bright part and faint part. It's continuously changing. Nature is really like that. So therefore, people who selected this one, I think I would say you have a sense of astronomy. So nature is usually something like this. So this looks like a very sharp edge, right? So this looks like an artificial signal, looks like. But for this particular case, actually, so this signal is really the from first radio first. So actually, I said okay. So this is true signal. So in this case, actually, this first radio burst is very bright within very short time scale. So therefore, it looks like a super sharp in data. Anyway, so in the past, the astronomy people get confused with between this microwave and the thermos. Nowadays, they established how to differentiate this. Okay? And then this is just an advertisement. So recently, I was involving with this project in Japan. So in Japan, we detected this first radio burst, mysterious burst from the space. We detected this burst in Japan for the first time. So we do detect this detection, clear detection here. Actually, there are so many detections so far. So this is a memorial detection only for Japanese people. This is not really special, but this is special for Japanese researchers. So therefore, this was featured in Yahoo News in Japan. That was great. And the question is, what is this? Nowadays, so there are so actually, okay, point is the origin of this mysterious fireworks is still unknown. So that's why astronomers are struggling to find the origin of this first radio burst. But we can imagine that there are several candidates using already known the astrophysical sources here, say white dwarfs, neutron star binary system, or stellar mass black holes, magnetar, young pulsar, supermass black hole, or supernova luminance. There are so many. So basically, astronomy people, they are trying to use already known population to explain this mysterious signal. But interesting thing is, there is another paper who is proposing this alien theory. But this is not major stream in astronomy, of course. But for astronomy people, I think we have to consider the astrophysical sources first, because we know that they exist. They do exist in the universe. So therefore, let's try to use already known population to explain this astrophysical first. This is from our point of view, astronomers' point of view. But some people can propose yes, alien theory. There's a paper about this. So therefore, in here way, maybe I have to list it here. We don't know which is the case, but most likely, we believe that most likely there's no confirmation, but most likely we expect that magnetar is the source of this mysterious first radio burst. What is magnetar? Magnetar is extreme object. So this is a remnant of supernova, which is composed of neutrons. And then interesting thing is, this is a really compact object, say 10 to 15 kilometer radius, very small in astronomy. But the mass is more than the sun. It's more massive than sun. And then, which has very strong magnetic field. So I can demonstrate how extreme it is. So this is a simple figure showing the size of the sun and also size of the Earth here. So our size is super large compared to the size of the Earth. Can you see this? The Earth is here, very small. And then this is a comparison between Sun and Earth. So this is saying mass is say more than sunlight, but the size is 10 kilometer. That is much smaller than size of the sun, size of the Earth. If I magnify the Earth here, okay, let's zoom in Earth. In this size, 10 kilometer is, I guess in this map, I think this is Taiwan. I'm not sure. It looks bigger. I guess emphasized. Okay, it's 10 kilometers this size compared to the size of the Earth, right? This is saying that within this tiny dot, actually there's a mass which is more than the sun, more than sun. more than the sun, this mass is confined within this very small region. So this indicates how extreme it is. So therefore, first order burst is really extremely high energy explosion. So therefore, we need to use extreme object to explain that. So that's why people are guessing, oh, this is probably the candidates of origin of FRBs. Another quiz here. And so how many minutes do I have?
Until 9:50. So
9:50.
20 more minutes.
Okay, okay. One more quiz. This is a famous quiz. So you can imagine that you take one spoon of neutron star, magnetar, just one spoon. So you take only small piece of magnetar, only one spoon. What is the weight of this one spoon of neutron star? So please think about it. You can guess. I give an ABC option here. A, 1 ton. B, 1 million tons. And C, 1 billion tons. And then CA, this is just an example. Total mass of the human. I don't know how comparison. I just come up with this one. Comparison. When I calculate the total mass of the human, assuming that 50 kilogram per person, now we have 8 times 10 to the 9 populations in the world. So therefore, total mass of the humans is about 0.4 times 10 to the 9 tons. So which do you think? Who thinks A? A? Who thinks B? Or who thinks C? Oh, maybe good. Or you can imagine that when I try to ask something, the answer is usually most extreme case. In this case, yes. The answer is here. Extreme case, yes.
Because you showed the line there.
So I have to hide this. Yes, I wanted to compare this data. Yes, yes. That's the mass of this one spoon is 1 billion tons, which is more than the total mass of the human beings. That's a lot. This indicates how extreme it is. So this is a possible origin, possibly the origin of FRBs. Okay. Then we are trying to confirm this from observations. But now, apart from the origin of FRBs, actually this is the most exciting part, I would say, of this FRB science. So why people want to understand FRBs? This is because FRB are supposed to be very useful to understand the universe. So let me explain some examples here. I think according to the time limit, I guess I can explain one of them, I guess, maybe one. Actually, FRBs are used to address many important questions in astronomy and astrophysics. I just selected. So one is missing baryon problem. So I explained this. So this is related to this electromagnetism data. So let me explain this. Why this is important? So first of all, missing baryon problem. What is baryon? Baryon is just a terminology in astronomy. Baryon is really just a very simple. It's just an ordinary material that we well know. For example, all the entity here, objects, are made by atoms, right? Atoms. Atom has these nucleons and the surrounding electrons making this structure. So this we well know this. Proton, neutron, electron, these atoms. So this is a baryon. Baryon is ordinary material that we know already. So we well know this behavior from the quantum mechanics. I think the most famous consequence from quantum mechanics of this baryon is, I think this is black body radiation. This is, I don't know if you learned this one in the class, but this is one of the consequences from quantum mechanics. If you use quantum mechanics, apply to the baryons, ordinary material, then you can predict the spectrum of sun. This is intensity or brightness of the sun as a function of wavelength. So you know wavelengths, I guess. Wavelengths corresponds to different colors of light. Red color, longer wavelengths. Blue color, shorter wavelengths. And then, what we observe from the sun is, I think, this yellow line. So sun's solar spectrum is this yellow. And the quantum mechanics predict this curve, smooth curve. So they are almost the same. So basically, quantum mechanics can tell you how bright objects are. So this is telling that if you have temperature, you are radiating emission. The sun is very bright because temperature is high. This is quantum mechanics. Then we use this in astronomy. So that means we know that well-known this baryon, behavior of baryon. So that means we know that they emit radiation because they should have non-zero temperature. Once they emit the radiation, we can use a telescope to detect them. Then we can count how much baryons we have in the universe, okay? Because we know behavior this. Okay? So we can observe baryons, né? Because of electromagnetic waves. Okay, that's okay, right? I mentioned this. Then let's compare. Actually, from another approach, I don't really mention this. From another approach in astronomy, actually we know, sort of, we have idea about total amount of baryons in the universe. We know this. I don't go to the details about this, but we know from different approach. We know this pie chart already. 100% of baryons. We know the number. But using this radiation, something like this, we can count how much baryons we have in the universe, which is shown by this blue here. So what we can observe is actually not 100%. Actually, there is a significant fraction of baryons are missing here. Then this has been long mystery in astronomy. Somehow we expect this 100% by chart, but only we can observe this. There's always missing baryons. So this is a missing baryon problem. So we are missing from observations. We are missing baryons from observations. Then people is guessing that maybe this missing part is plasma in intergalactic space. So let me explain this. What is this? Plasma. So this is a picture of the universe. So you see the bright dots here. They are all galaxies. When you take a picture, it's bright because they are emitting radiation. Now you see space between galaxies. It's dark. It's black. Right? Black means we don't detect anything in that space. It looks like empty. We cannot detect electromagnetic wave from intergalactic space. That's why it looks dark, black. So that means we can only observe baryons in galaxies. We can, if there is a baryon in intergalactic space, that we are not observing. And then expectation is there are lots of baryons in the form of plasma in intergalactic space. But plasma is ionized material. We expect that there are so many plasma in intergalactic space. But problem is plasma doesn't emit electromagnetic waves. We cannot directly observe plasma in intergalactic space. That's why it looks like black. So that's why we are missing this plasma. Plasma is baryon. That's our expectation. We don't know. But this has been huge problem in astronomy. But now game changer arrived. So that is FRB. FRB is a new object in astronomy. FRBGD game changer. So let me explain. This is, I think, related to electromagnetism. So let's say FRB happens at this distant galaxy, and then radio emission comes from this galaxy all the way to the observer here. Or let's say we are standing here, our galaxy here. So radio emission comes here, propagates from here to here. So then, what we expect is actually this in intergalactic space. It is not completely vacuum. We expect there is a lot of plasma here. If you have plasma, actually we have now theory here, general physics. According to the electromagnetism, speed of radio emission can change within plasma. When radio emission propagates from here to there, so this goes through inside plasma, and the speed of light inside plasma changes actually depending on the frequency of radio emission. If frequency is high, it can keep original speed of light, then I would say relatively faster. If radio emission is low frequency, it's more affected, and then it becomes slower. So therefore, let's say there are two radio emissions coming from FRB, high frequency, low frequency. They start at the same time, and then to come to us. But speed of them are different inside plasma. So therefore, so their arrival time changes. So then we expect a time lag between high frequency, low frequency. Okay, ma? We expect time lag. The high frequency comes fast. Low frequency comes late. This is our expectation. Then, when we detect FRB, so this is a typical example of detection of FRBs, we do see the time lag actually. Y-axis frequency, observed frequency, x-axis time, observed time. See, for example, this is 1.5 gigahertz. This is, let's say, higher frequency. And this is a signal. So higher frequency comes this time, maybe 100 milliseconds. Low frequency, 1.3 gigahertz, actually arrive at, say, 300 milliseconds. So this comes late. So therefore, this is saying that high frequency comes fast, and low frequency comes late. So this is exactly what we expect from plasma theory. Then, this time lag, how much you have time lag from here to there? Actually, this is proportional to the how much amount of plasma you have between FRB and the observer telescope. So therefore, by using this time lag of FRBs, actually you can directly measure this plasma in intergalactic space, which is supposed to be missing baryon. So now we have direct proof of missing baryons. And then people expect, okay, now we can resolve this missing baryon problem using a fast radio burst. Then let's see the results. And this is not our paper, but this is a very famous paper in this field. Y-axis is amount of the plasma in intergalactic space, Y-axis. And then X-axis is a redshift. I don't know if you learned redshift, but say this smaller number corresponds to nearby universe, larger number corresponds to distant universe. And the point is, so using fast radio burst, you can directly measure this plasma in intergalactic space. So that is shown by these markers here, different colors here. There's also theoretical prediction here, assuming that missing baryons, they exist in intergalactic space in the form of plasma. Then see, so actually this is a theoretical prediction. Actually what they observe is really consistent with this theoretical prediction. So therefore, so this is saying that basically missing volume problem is resolved because now you are observing missing volume problem in y-axis. This is exactly consistent with theoretical prediction. So this long-lasting problem actually recently has resolved, I would say. And then, I don't have time. Next key question is, so now total amount is okay now. They resolved total amount of missing volume. So we resolved. Next key question is, there must be so high density missing volume or low density missing volume. There must be fluctuations in the universe. It shouldn't be completely homogeneous. So universe is inhomogeneous, right? This is high density region, low density region. We really want to understand this more variance toward this direction or less amount of missing variance toward this direction. So we want to understand this variation in the universe. That maybe really completely answer to this missing variance problems. Then our students, I really respect the students at NTHU, and also I was surprised to see your presentation today. So you guys are really high level. I'm so surprised today. She's also one of that good example. Actually, I am collaborating with Tsuin Shu at NTHU. She's an undergrad student here. This is confidential results. Please don't take it to other people. She compared, she derived, she measured how much missing variance you have compared with average number. So y-axis is indicator of how much missing variance you have along different directions of sky as a function of number density of galaxies. So then she found that along the direction toward the place that have more galaxies, actually missing volume also exists more. But if you look at the less dense environment, less dense region in the universe, there are less galaxies. The missing volumes are also less. So actually this is really natural. So because if you have more amount of materials, then you expect more missing volumes over there. But this is really natural and theoretically predicted long time ago. But this is the first observational evidence of this fluctuation of missing variance. So we found this first observational evidence. So therefore we submitted the paper. And I think I don't have time, so I finished here. So I scribbled so many, but I don't have time. So therefore, I think I stop here and I take questions. Sorry. This is conclusion.
Okay, thank you very much. We still have 2 minutes, so any quick questions?
What gets you interested in studying physics?
Good question.
Oh, it's a very good question. I just like the physics or science when I was junior high. And then after that, I really wanted to astronomy because when in my generation, Hubble Space Telescope was really cutting edge. You know Hubble Space Telescope. They keep generating very beautiful images of the universe. That amazed me, and then that was my that makes me to decide go to the astronomy field.
Okay, I think it's about the time, so let's thank Professor Hashimoto again. Group 7, please prepare for the Tuesday next week. Today, I need to take your attendance. So I'm going to leave it here, or maybe here. So please mark your name here before you leave. Don't mark your friend's name, okay? Okay, then see you next Tuesday. Have a good weekend.
You are very good. Thank you so much. Did you make it from scratch?
Yes.
Really? That's great.
Oh, the game.